So about instability and oscillation reaction networks, for people who were maybe a couple in the audience 1 month ago in Linz, I gave basically the similar or the same talk, so to tune concentration. My interest is to find periodic oscillation in dynamical system arising from reaction networks. Here S is stoichiometry matrix and R is the vector of the reaction rate. And the problem is, of course, that methods are limited to the number of the species, to the dimension of the system. And in a reaction network, potentially they are quite large. And as well, of course, parameters. Let's say for mass action is at least 1 for reaction. So it is 1 for reaction, and reactions are on the same order, the species at least. So this is a problem. There are the standard methods in the literature. I do not cover all, but let's say the most used are local Hopf bifurcation, where you have to compute a steady state, so a fixed point with a purely imaginary eigenvalues. And then you have to check also other things like transversality condition on the general C conditions, but even just locating the point by Ruth-Hurwitz computation is something which becomes, let's say, on the verge of being undoable with species maybe 5 or 6, or dimension of the system maybe 5 or 6. And if one wants to check Lyapunov exponent, it's even worse. The number is even lower. A second possibility, which at least is a bit better computationally to finding candidates, is Takens-Bogdanov bifurcation, like you have like Hopf bifurcation, you have purely imaginary eigenvalues, and the limit when the imaginary part goes to 0, you have a algebraically double, geometrically simple eigenvalue 0, and that's a Takens-Bogdanov point, and it's computationally easier to find because you have determinant 0, and also the previous term. So it's a bit easier to find, still difficult to compute transversality condition and so on. But moreover, of course, you have situation where you have Hopf, but you don't have Takens-Bogdanov. So basically is a selection of very specific system, which I will comment in a moment, undergo both multistationarity and oscillation, the Takens-Bogdanov case. And is in a way the connection of the two. Poincare-Bendixson is a very elegant argument when it works, namely for dimension 2 or something which is like dimension 2, where there is a special structure and you can kind of project into dimensional space, like monotone cyclic feedback system. So again, you have a dimensional problem. In the community, a lot of work has been done on inheritance results, which are basically perturbation arguments. So one studies a small structure and then enlarges. And for all the case, so this is not a general complaint, it's just an effect. So when you do perturbation argument and you get for bigger network, then you are kind of approximating the bigger network in a way with smaller network. So one may miss oscillation which appear because one has a larger network, so to say. And the second issue, which is actually very interesting, I guess, research direction, is how for big network one finds the smaller one. So how to reduce the network by the rules which these results have. And the last, which I will pick today, so to say, are kind of global methods, so topological methods relate to local Hopf bifurcation, but they are in a certain sense in global setting, brutalized as intermediate value theorem. I will speak in the next slides about this. And the problem here is that one has no regularity of stability information, contrary to the local Hopf. So if one wants to study stable periodic orbits, you are back to the local Hopf. There is no gain here. One should argue or not argue that maybe stability, we should not be obsessed by stability, but stability one needs to go local. And the main result here is, to use is a result by Bernard Fiedler in his PhD thesis of 85, so published also in an unusual journal in Crelle. But I know this result, which was stated originally for parabolic PDEs, so a bit with formulation which is a bit obscure, let's say, or at least a difficult digestion for people not in the area, because he happens to be my PhD advisor. So then that's how I know this theorem, even though it took me a while to understand what this theorem was about. And I translate here, let's say, the statement to be more digestible in this occasion. So basically the point he says, okay, you take a vector field which is analytic. Now analytic for reaction networks is a rather friendly assumption, of course. And then one has an analytic parameterization of a family of steady states with one parameter. And then you have only one real condition to check, so like two actually, of course, that the first is invertibility along the path. Invertibility, so the Jacobian of the steady state is invertible all over. And then you do not need to find any bifurcation point, it's just a degree argument. The proof is absolutely non-trivial, but the degree argument says, well, if you start at the start and the end point, you have different stability. Then somewhere you have periodic orbits. Maybe you have many different continua of periodic orbits. We don't know how many, how the parameter, the family of steady states bends along the purely imaginary axis. But you have periodic solution, non-stationary periodic solution. This is based on this theory, which is relatively well known in different community developed by Choma, Lepare, Yorki, among others, on global Hopf bifurcation. And the advantage, and why this is much more handy, is that you do not need to check any parity resonance transversality condition, and moreover, let's say, frees us from the need of computing the bifurcation point. So this is a result which does not require the computation of the bifurcation point to conclude per periodic orbits. And the trick is really analyticity, because in principle, it could occur that you even have something very, very degenerate like continua of points with purely imaginary eigenvalues, and this is done to handle this. This assumption handles this. Good. So I want now with this also make a comment, with this theorem also make a comment as a bifurcation perspective on multistationarity and oscillations. Something which everybody who work with this, of course, knows, but I think it's good to state at this stage in this way. So a bifurcation approach is, okay, you have a stable equilibrium, stable steady state, and stability is lost. How it can happen for real systems? Well, it can happen either via a real zero, going through the real zero, or through complex pair of complex conjugate eigenvalues. Of course, you can have all combinations, but let's stay easy for now. And basically, the comment is that multistationarity appears really when you have a real zero eigenvalues. And in certain setting, one could argue as a characterization. And because of the Fiedler's theorem, also oscillation, I mean, can happen also without this. But bifurcation, like a steady state bifurcation wise, they will happen anytime you have pure imaginary eigenvalues in the setting of the Fiedler's theorem. And here, from an historical research perspective, we know as a community everything, not everything, sorry, not everything, a lot of things, so to say, on multistationarity, in the sense that in the last two decades, a lot of work with mass action, with Michaelis-Menten, so with other general kinetics was done. In Italian, life and times, we say vita, morte, miracoli. In Italy, I don't know why we always put some, so I can guess why, we always put something related to the church or in all these proverbs. So we say life, death, and miracles of multistationarity. So in this sense, okay, but we especially know, and that's how this body of work on multistationarity started, especially we know when multistationarity does not happen, like injectivity, concordance, this kind of concept. Well, if you have this type of conditions, then instability, it's really if and only if with oscillations. Because from the bifurcation perspective, because of Fiedler's theorem. And vice versa, if you do not want exclusion, so you don't want Hopf bifurcation to happen for monostationary network, of course, you don't get any instability. So you don't get any unstable steady state, and you have something which I call universal stability, like locally stable independently of the choice of parameters. Good, and now I want to say, okay, how we can use this for reaction networks. For reaction network, the Jacobian has a very interesting structure and very convenient to apply this result, because the steady state condition because of this, the natural structure, can be interpreted as a linear condition. Like the reaction rates must be at the steady state flux vector, namely steady state flux vector, namely in the kernel of the stoichiometric metric. Now, what is, if you want to write the Jacobian, you have to write derivatives. I do this here for explicitly for a monomolecular Michaelis-Menten nonlinearity. For b equals 0, one get the mass action case. If you get just to give an idea, a concrete example. So the derivative here of the function can be expressed by a simple trick, namely multiplying by identity x over x here. The derivative is expressed as a function, 1 over x, and here, if you have Michaelis-Menten, 1 plus bx. Now, at steady state, that's very, very convenient because basically the upper part, you can reparameterize. You can think that this is actually just one entry in a kernel vector of the stoichiometric matrix here. So in a way, it does not really depend on x. And similarly, because here you have a b, also this you can rescale b, 1 over bar x, essentially. So you have that also this term in general does not really depend on x. So then you have factor out 1 over x. And this happens for all the derivatives. And if one works this out, like in stoichiometric network analysis, I think originally Bruce Lee Clarke did for convex coordinate here. If you write this in convex coordinate, the flux cone, then one gets that you can write the Jacobian as a matrix, which does not depend on x, and a diagonal matrix. And if you think about 1 over x as parameters themselves, then you are really here, you see, you are really a matrix times diagonal matrix. And then again, I always do the first simple basic case. Let's start simple, no conserved quantities, assume that B is invertible. Like you have maybe a lot of degradation, whatever, just for simplicity now. Well, the determinant of the sign of the determinant of the product of these matrices by Binet depends only on the determinant, the sign of the determinant of B. So which means that if you play with D, you don't get any drop in rank. You don't get any real zero eigenvalues. So this means that if you have D1 and D2, for which you have the Jacobian at these two terms, which are, for example, stable, unstable, but any different configuration of stability, then you get periodic orbits. Now one could, one could write the theorem very abstractly like that. And still, I want to say that this, of course, the problem is how I find now this stable and unstable. One say, yeah, okay, and now how you find. True, it's a very fair complaint. But on the other hand, if one finds numerically these two, then one proves analytically the existence of periodic orbit. It's not numerics. I mean, what you can find with numerics is like kind of computer assisted, if you want, type of proof. You find two places in parameter spaces, which you can then show they exist. You can just check, they exist with different stability. And this implies analytically, so no numerics, implies analytically the existence of periodic orbit somewhere. Still, of course, one wants to have maybe nicer conditions. So nicer conditions, or at least easily readable, I found that the more natural way to do is via this P minus matrices, which is a bit a curse because you have to write P minus 0. They were called Higgsian in economics at a certain point. So I may say P instead of P minus 0. Apologies. So because P is for positive, but then you do the minus P, which is the stable case. Anyways, P minus matrix is a matrix where all K principal minors have the stable sign, minus 1 to the power of K. Think like minus identity, this type of thing. And zeros, you can have also zero minors. D stability is a generalization of Hurwitz stability when you require that the eigenvalues are always with a negative real part for all choice, for all the products. So the AD, the product for any positive diagonal matrix D, is always Hurwitz stable, always stable. And you have basically here two results which are completely absolutely complementary one to each other. So one says that if A is stable but is not a P minus 0 matrix, then you get purely imaginary eigenvalues for a product, which in our hands should say if the Jacobian is stable but not a P minus 0, then you get periodic orbits. That's how we shall think. And the reason is basically just that this stability, a necessary condition for this stability is that the matrix is P minus 0. It's a necessary condition, relatively straightforward to prove. And then the change of stability along a parameterization A, namely I times identity, and AD for which AD is unstable, brings different spectrum. Intermediate value theorem, you find purely imaginary eigenvalues. And there is the other direction I found very interesting, that you have basically opposite, complementary, which says if a matrix A is an unstable P minus matrix, so now it's, before was stable but not P minus matrix, and here is P minus matrix but not stable, or better, unstable. Then same argument, you have purely imaginary eigenvalues for a product. Reason is similar, is just that this Fischer-Fuller proved a beautiful theorem in 58, this is Age of My Mother, and which is basically that you get that if A is a P minus matrix, then you can multiply by a certain positive diagonal matrix D, so that AD has all negative real simple, actually here, eigenvalues. So again, you do the same trick. Now you start from unstable with identity, you go to stable, and you have this trick with purely imaginary eigenvalues. Interpreted in terms of the Jacobian on that expansion. So if you say, okay, now the Jacobian is stable but not a P minus matrix or an unstable P minus matrix, then you get periodic solutions. Okay, with conserved quantities a bit trickier, and one should look at the principal submatrix and maybe at the principal submatrix of the largest dimension. But I do not want to enter this technicality here. I want to say something else, namely, of course, again, one can complain, say, yes, but how now you have this condition? How you characterize this condition from the stoichiometry of the network? Of course, G is in itself a stoichiometric object, but I do not want, I mean, you ask, okay, now come up with an example for which this is work now. And can I or can I not? And the answer is that for mass action, the situation is difficult. It's difficult because you have less parameters to play with. So one can, and it's open, so I do not know the answer. And I'm very interested in this answer. So for one, at least one necessary condition, indeed, because you know injectivity, you know this condition cannot hold if you want the Jacobian not to be a P minus matrix. So you have this condition by Banagi, Krechun, and so on. One can work a bit at this, but not sufficient, not sufficient. And with B, I have some hopes that it is similar to Michaelis-Menten, as I will show you now, but I have absolutely not done this precisely. So I rewrite here for mass action the theorem, and now for Michaelis-Menten, or in general what we call parameter-rich kinetics, which includes Hill model, generalized mass action, so a big class of kinetics. Then you have the same conditions, but now the same condition can apply to any square submatrix of the stoichiometric matrix with negative diagonal. So you reshuffle or you relabel, if you prefer, the network. And then you find any square submatrix with negative diagonal, which has these two conditions, stable but not a P minus matrix, or unstable P minus matrix. And then you get periodic solutions for the Michaelis-Menten generalized mass action system. Why is, again, in a way, I don't call it inheritance, but it's also a perturbation argument with the same issues which I claim at the beginning, I complain about, in the sense that you, again, approximate in a way, you blow up on the matrix, 2 by 2 matrix, and you approximate, or maybe 3 by 3 at least, matrix S kappa, and then you kind of approximate the behavior of the full Jacobian, potentially with 1,000 species and dimension with a 3 by 3 matrix. So there's the same problem. But this is done only at the linearization. So it's only the linearization. And yeah, and this way, we had this thing, and we were curious now. So this is a work with Alex Blokhuis and Peter Stadler, I didn't mention. And so basically, we were interested in the minimal ones. So maybe one wants to compute sooner or later these matrices which have this property, and it's good to look for the minimal one. Also because they offer an interpretation. So minimal here means that this matrix satisfies such property, but no principal submatrix of such matrix does. And if they are minimal, satisfy property 1, we call oscillatory cores of class 1. They can be interpreted as having a positive feedback. So P minus 0 matrix, not be a P minus 0 matrix means somehow that you have a positive feedback in the matrix. It's because you need to have a sign which is yeah, positive feedback. Again, for discussion. And also they are both autocatalytic and non-autocatalytic. So here, autocatalysis sits in this situation. While the oscillatory cores of class 2, which satisfy the other property, they have negative feedback and they are never autocatalytic. But they often follow something which I will comment on now 1 second, called principle of length. And yes, and we had basically a list, which is like not a classification. So it's a classification, at least not in mathematical sense. So it's not an exhaustive classification, just to see that you can build up many of those. So this means that any network, for example, containing this list of reactions will admit oscillations under parameter-rich kinetics under Michaelis-Menten. This is for the class 1, and this is for class 2. And then I wanted indeed to say, because in class 2 you see this square pink, and I want to say about principle of length, which happens mostly for class 2. So the point is that if you start with a negative feedback, let's say this kind of feedback, minus 1, 1, minus 1, minus 2. No, sorry, there is my daughter came. Yes, so minus 1, minus 1, 1, minus 1, minus 2 is stable as well, and in this case, so it will not work what I said. They are P minus matrices, but they are stable. But it happens, curiously, or maybe not so curiously, that if you add intermediates here, and probably you can add in other positions, enough monomolecular intermediates, so that's a simple path, like this, then at a certain point it becomes unstable and oscillation appears. So this is also to say that if one want to look at this, the too small one in this case will not give you oscillations, but only the big one will give you oscillations. Here you get oscillation at a certain point. For this very simple example here, it's clear because you have a closed formula for the eigenvalues. So it is clear why one gets oscillations here. Because you can, it's kind of like a similar argument with the roots of unit. You get, you have a circle, and you get that the roots of units get more, let's say, more crowded, and at a certain point they have to eat also the real positive part. I think the same intuition works also for the other, but there is no obvious proof why this happens. But it happens for all those examples. And to conclude, I just show now 2 examples with the same intuitions, exactly the same intuition which work for mass action. And then, so basically here you can see positive feedback is what I call is a 3x3 here. And this has a determinant of sign minus 1 to the power of 2. So as a real positive eigenvalues, this one. It's not a P minus, is not a P minus 0 matrix. And this one here has a P, is stable. And then it works. But, and it works also intuition. You see that I have really to make this positive feedback here dominant. These are down, are the species A, B, and C. And I really put 1 over A, 1 over B, 1 over C, A, B, C. I put them small enough so this became dominant. This works, is all nice, but of course was trial and error. So why this combination specifically works, I do not know, or at least I do not understand. Why this and not if I only put here 1 instead of minus 1? This will not work, and I do not know why. So it's not clear. I just tried a bit, and this was a nice example. While for the negative feedback, you get the complete similar intuition as the Michaelis-Menten, with the interesting twist that the length for mass action, you need to add more steps. Again, I do not really, so it's more intuitive, but I do not have a complete answer why this happens, so I didn't think enough about this. But n needs to be 6 for, let's say, Michaelis-Menten, and needs to be, I think, 9. Maybe I'm wrong, but something like that for mass action to give oscillations. So yes, this basically is almost all. These are the two references. For mass action without the stoichiometric interpretation is this paper, and with Alex and Peter for parameter rich went out on archive a month ago, where you also get the stoichiometry story. And the last comment is basically I want just to point out a standing conjecture which was stated with Peter Stadler again in our first collaboration in this paper on universal stability. So basically, when a network does not admit at all, consistent network, so a network which admits a steady state, does not admit at all for general monotone kinetics any steady state which is locally unstable. And we conjecture that this is, so it's equivalent characterization for not having any square sum matrices of this with negative diagonal up to relabeling, which are D unstable. So absence of D unstable matrices like that, if and only if universal stability. One side is relatively easy and proven. So it's proven that if you have universal stability, you cannot have for Michaelis-Menten parameter rich, like generalized mass action and so on, not for mass action, but for more general kinetics, you cannot have any square matrix like that. But the other way around is not known. And what it is, what you have really to do to prove, which will be valid also for mass action, is essentially to try to exclude Hopf bifurcation for networks whose Jacobian is a P minus matrix or P minus 0 matrix. So this is really an Hopf exclusion problem. And because in the literature and in the community, there is a lot of interest to exclude Hopf bifurcation from networks which are not with, which was Jacobian admits multistationarity, so is not a P minus matrix. I want to say that maybe this is the first step to understand whether this holds, because that would be also a Hopf exclusion result in a way. Yeah, so that's it. And I thank you for that.